before our new class, I want to talk about the homework problem which is due today. And this is the section 3.3 homework for 3.3. Okay, we have students ask me to help. So this is the number one. Okay, number one, which is the true-false problem. Again, the true-false problem. If it's true, you just say, okay, it's true. You don't need to give me any proofs. Okay, but otherwise it's too complicated for you. Okay, and if it's false, you just give me the counterexample. Can you give me an example to show this statement is not true? Okay. So this one, which is the number 1B, okay, number 1B. It says, okay, for any function f, which is from 0, 1 to r, then its image, which is f of 0, 1, right? This is we use this notation to denote its image or its range, is an interval. Okay, so actually this problem is also related to the theorem 3.14. Okay, we didn't prove that theorem, but we say, okay, if a function f is a continuous function, then this is an interval, the domain is an interval, then the image would be also an interval, right? But here, this statement is say, okay, any function, so it must not be true, right? So it's false. So this is the problem is false. Why? So you need to give me, for the false problem, you always give me a counterexample, okay? Not just illustration, right? You cannot say, okay, because the theorem didn't say continuous, they say continuous, and you here didn't say continuous, so you must be wrong. Maybe this statement is true, we just cannot prove it, right? So if you can give me a counterexample, that means, okay, this statement must be wrong, okay? So the false problem. So this is the one thing, okay? Any function. So you can you make the function which maps 0 to 1 to r? This is the function. The image is not an interval. If you can do that, right? Then the statement must be wrong, because statement says, okay, the image is an interval. Okay, so this is the function I have mentioned in our class when we talk about the continuous function, so which is called the tertiary function. What's that? Okay, this is the function which will map all the, so to be 0. Okay, no, yes, all the real numbers, not real numbers, it's the rational numbers, okay? Rational numbers. Rationals. So here our domain is 1. So let's just say, okay, maps all the rational numbers in 0, 1 to be 0. Then all the irrational number in 0, 1 to be 1. Okay, so this is called the tertiary function. Okay, so you don't need this one. Okay, you just say, okay, it maps the rational number to be 0 or an irrational number to be 1. Okay, then we fix this function under this domain 0, 1. So all the rational numbers in the 0, 1 will be 0. Okay, all the irrational numbers, the f value would be 1. So you can see what is the image. Image is 0 and 1, two discrete numbers, right? So that is the image of this f. Sorry. image of this f is number 0 and number 1. This is not an interval, right? This is not an interval, just two numbers, not an interval. Interval means we have several numbers together, right? We have some the upper bound and the lower bound, right? This kind of things. So this is not an interval, okay? So that is a very, so every time you need to think about, if it's not a continuous function, that is a very good example for many problems, okay? So number C, okay? We say that for any, still number 1, C, okay? This is number C, this is the continuous function, f. F is continuous, right? Continuous. That is from D to R. Then the image f of D is an interval. Okay, so this is again related to the theorem, the same theorem, 3.14. It says for any continuous function on the domain is an interval, then the image would be interval, right? So now we see this function the f is continuous and the domain is D, and then the image would be an interval. So there is one thing, one condition missing, which is this D should be interval, right? But you cannot say that, okay, maybe it's correct, we just cannot prove it, right? So, but you see, probably this would be false. So can we find the example, right? Okay, let's find this example. Let's take D. Okay, so we just don't take the D to be an interval. We take D to be 0, 1. It's a discrete two numbers, right? They're not interval. Number 0, and number 1. And the f, we just take any continuous function, x, right? Fx. So what is the image? This is the continuous function, no problem, right? It's a straight line, right? It's a straight line, of course, it's continuous at 0 and continuous at 1, right? So this is the f of D. What is f of D? F of D, when x equals 0, it would be 0. When x equals 1, it would be 1. This is not an interval. It's not an interval. So this is false. Okay. Again, if you think the statement is wrong, okay, you just need to give me an counterexample. Okay. Counterexample. So this is the two problems. Yeah, some students have trouble with. So any other questions?
For that one, I did 1 over x with D being from -infinity to 0. And then
If you take net 1 over x?
Yeah, as a function, and then I put D to be basically...
You cannot take 1 over x because 0 would not be in the domain. Right? Yeah. You cannot plug in 0 because the 1 over 0 is undefined.
But that's what I broke up D because I was trying to...
you can take a D to be 1, 2, and f of x equals 1 over x. That's fine.
Yeah.
Yeah, that's fine. Yeah, you can make any counterexample you want, just to state this statement is wrong. Just illustrate this statement is wrong. To show the statement is wrong. That's okay. We have infinitely many counterexamples, right? So here is just one example. Right. So since the statement is wrong, so that means you always can find infinitely many examples, but but you just give me one example to show this statement is wrong. Okay. Any other questions? Okay. So today we want to talk about the, let me see, this is the yeah, 3.5. 3.5, which is called epsilon delta criterion for continuity. Okay. So in other words, we want to use the epsilon delta language to describe the continuity of certain functions, okay, of functions. So before that, let's recall the definition for the continuous function. We're using a sequence, a convergent sequence, right? So here's the definition. Let's recall the definition for the continuous function, which says, okay, f is a function which is from D to R. We say this function is continuous at A is a point in D, right? Which is a point in D, if for any sequence AN in D, the sequence converging to this number A, then the sequence which is f of AN converges to f of A. So in other words, the limit n approaches infinity of f of AN is equal to f of A. Then we say this function is continuous at the point A, x equals A. Okay, so this is the definition. So this is the definition we have learned at the beginning of the first section in this chapter. So now there is another way to define the continuity. Okay, before that, let me give you what is the epsilon delta criterion. Definition. We say a function which is from D to R is satisfies the epsilon delta criterion at A, which is a point in D. Okay, what does this mean? Epsilon delta criterion at A. It means if for any epsilon greater than 0, there exists a delta greater than 0 such that when x minus A is less than delta, okay? When x minus A is less than delta, fx minus f of A is less than epsilon, okay? So this is the epsilon delta criterion. So for any epsilon greater than 0, there always exists a delta greater than 0, such that when x in this interval, what's this interval? This is the remark for the remark is that this is x minus a is less than delta. That means x is between a plus a minus delta and a plus delta, right? So when x lies in this interval, then f of x minus f of a must be less than epsilon. For no matter how small epsilon you will have, okay? So now let's look at a graph, okay? The graph meaning for this criterion. For example, okay. Oh, sorry, I should have one more thing. There another one, this is fx minus f of a less than epsilon. That means f of x should be between f of a minus epsilon and f of a plus epsilon, right? So you should be very familiar with these two equivalent form, okay? One is using the absolute value, the other one using the not inequalities without the absolute value, okay? They are actually the same thing. Okay, so now let's look at the graph. So this is the graph, okay? This is the graph. And this is the, for example, A. Okay, so this is the f of A. Then we pick arbitrary epsilon, okay? And here. This is f a plus epsilon. So in other words, here is epsilon. And we have f of a minus epsilon. So here is another epsilon. So this is the f a minus epsilon. Okay. If this function satisfies the epsilon delta criterion, it means you can always, I use another color, draw a box, okay, a square box, which has the center is f of a. We can always draw a square box. The center is f of a. This box, then you can see that all the f values, right? If you take different two numbers, okay, two f values, you take the difference, okay? And then take an arbitrary number, okay? Arbitrary number here, you take the difference between f of a and that number, it'll always be less than epsilon, right? If the number is here, right? This number f values minus f of a is less than epsilon, right? Because it's between the band, right? Between this band, two epsilon band. Okay, and this box, if you look at this one, here is a plus delta, and this is a minus delta. So in other words, this box is determined by the delta, okay? And here is two, this is two, this is delta, and this is also delta. So for the different epsilon, this box is different, right? You must have, for this epsilon, you must have this box such that this curve get into the box and leave the box from the sides, not from the top and the bottom, right? If from the top and the bottom, the difference would be greater than, right? Greater than equal to epsilon. But if the curve enter the box and leave the box from the sides, then between it, you can take the difference between the f of a and the f of x. If x is the x lines in this interval, the difference must be less than epsilon because it's between the bound, inside the band, right? Inside the band. Okay, so this is this criteria tells you for any epsilon, you can always find this kind of box. This box has the length, which is 2 delta. Center, this is the center. Okay, this point is the f of a is the center, such that you can draw a box such that this curve enter the box and leave the box from the sides, not from the top or the bottom. Okay, that if you can do that, we can say this function f satisfies epsilon delta criteria. Okay, so if it does, we can try some smaller epsilon, right? No matter how small epsilon you have, you can always draw this kind of such box, right? Okay, for any epsilon, you can do that. Then we say, okay, this function f satisfies this epsilon delta criteria. So this is the criterion, this epsilon delta criterion means, okay? You can, for any epsilon, you can always draw this kind of box such that this box, the center is f of a, and this box is such that this box, the curve enter the box and leave the box from the sides, not from the top or the bottom. Okay. So this is the geometric meaning. So you can imagine if the epsilon is small, then this box would be very tiny, right? But you can still see that this kind of box exists. If you cannot find this kind of box, so that means it does not satisfy the epsilon delta criteria. Okay. So you can see that this delta is depending on the choice of this epsilon. Also depending on the values at A, right? Depending on the position of A. So it depends on two things. So the idea is, if we want to show that, show a function satisfy the epsilon delta criteria, that means we need to find for any epsilon and this A, we need to find some formulas for this delta. If you can find this delta, then we are done, right? Okay, so this is an example. Example, we want to prove this f of x equals x cubed satisfies the epsilon delta criterion at x equals 2. A equals 2, okay? So let's look at the proof. How to do that. So in other words, we needed to take any epsilon, that epsilon would be greater than 0. So that means epsilon is an arbitrary number, okay? So we pick arbitrary epsilon. Then we need to show that we need to find delta which is of course greater than 0, such that for the x values, which is x minus 2, is less than delta. So that means we centered at 2, and the length, you see, this is the center is A, and this interval, this is the interval, right? This interval is x minus A less than delta. Right? This interval is x minus A less than delta, which means between A minus delta and A plus delta, right? Okay. For x minus 2 less than delta, for this problem, we have x cubed, which is f of x minus f of A, which is f of 2, which is 2 cubed, right? Which is 8. This one should be less than epsilon. If you can do that, then we're done, right? So the key point is you need to find this delta. Okay, before that, let's look at what is x cubed minus 2 cubed. Okay, so since this is inequality, right? So we still like we did for the convergence for the sequence when we talk about the epsilon n, right? Epsilon n language. We also needed to find the n, right? So now we just needed to find the delta. Okay, so we still needed to play the inequalities, okay, all the time. So this one, x cubed minus 2 cubed, there is a formula, right? A squared, a cubed minus b cubed, which is equal to x minus 2 times x squared plus 2x plus 2 squared, which is 4. Okay? So why we want to look at this one, the reason is here is x minus 2. Okay? And the absolute value of x minus 2. Here we try to find some factors about x minus 2. So this is x squared plus 2x plus 4 times x minus 2. Okay? So it's equal to, it's less than equal to what? We put the absolute value for each term, right? We have the inequalities, right? Triangular inequalities for the absolute value, right? Ax is less than equal to this one, right? You remember that. Then we put for each one. Okay, we use this inequality again. Then you will have this one is less than equal to the absolute value square of x squared plus 2 times absolute value of x plus 4, right? Then this thing times x minus 2. Okay. So the next idea is, this is not good, right? Because we have some x. If we can replace this one by some constant, okay? So here, this one's idea. Let's consider for, if we take epsilon under, if we look at this one, x minus 2 is less than 1. Of course, you can take less than 2, okay? It doesn't matter. If you take x minus 2 is less than 1, so that means x is between 1 and 3, right? Then this inequality, this part, we just look at this, the parentheses part, okay? X squared plus 2x plus 4. This one, we can replace the absolute value of x with 3, right? 3 is the largest number we can take, right? This one is less than 3 cubed plus 2 times 3 plus 4. which is 19, right? Okay, so we can replace this one by this constant 19 when x minus 2 is less than 1. The absolute value of x minus 2 is less than, okay? So this one, x cubed minus 8, which is 2 cubed, right, is less than 19 times x minus 2 for if this is the x minus 2 is less than 1. Okay. So this is to be true if we take the delta to be 1, right? But we need this one is less than epsilon. We need this one is less than we need. Okay, I use the scratch paper. Okay, I use another color to describe this one. We use box. This should not be in your proof. Okay. We need this one. We need this one is less than epsilon, right? This is what we want. If this one is less than epsilon, then we are done, right? If 19 times x minus 2 is less than epsilon, then we're done, right? So 19 minus x minus 2 is less than epsilon, so that means it should be less than epsilon over 19, right? If we take delta to be epsilon over 19, so that means when x minus 2 less than delta, then this x minus 2 should be less than when x minus 2, this is our case, right? This is the thing we want. We want to find a delta. So now we take delta to be epsilon over 19. So when x minus this delta, minus 2 less than this delta, which is 19 epsilon over 19, then this x minus then x cubed minus 8 would be less than 19 times x minus 2, less than what? Less than epsilon, right? Because this is less than delta. Delta is, okay, I should write one more thing. So less than 19 times x minus 2. X minus 2 is less than delta, right? If we take the delta to be epsilon over 19, so this one would be equal to epsilon. Then we're done, right? Okay. So this is very similar to the epsilon n language, right? We needed to find a certain n numbers. So now we don't need the n to be, we don't need the delta to be integers, a positive, a natural number. We just say, okay, it could be any real number greater than 0. Okay, so this is the epsilon over 19 is a real number. So we don't need to take the integer part, something like that, right? We just say, okay, if we take delta to be epsilon over 19. Okay, so keep in mind, when delta to be epsilon over 19, this one would be less than epsilon, right? No problem. However, this one from here to here, this one less than this one, this is true for the delta to be 1. Okay, to be 1. So if we take the delta, so we need to make these two inequalities. This one is less than this one. These two inequalities. This one inequality and this inequality, right, to be true at the same time. For this inequality, this delta should be 1. For this inequality, this delta should be this one. We want to make these two inequalities to be true. The idea is we take the minimum values of this delta. Okay. If the minimum value, so we take delta to be the minimum value of 1 and epsilon over 19. Then we are done, right? If we take the minimum value, so this delta should be less than or equal to 1, right? This delta should be less than or equal to 1. Okay, less than or equal to 1, of course. Less than or equal to 1, delta is less than or equal to 1, x minus 2 must be less than 1, right? Because it's less than delta. So it must be less than 1. So this one, the 19 we can get, right? If x minus 2 is less than, okay, the delta is the minimum value. So that delta should be less than or equal to epsilon over 19. Delta is less than epsilon 19, so it would be less than or equal to epsilon. So it's still less than epsilon, right? So there's no problem. So we need to take the minimum values. Okay. Okay, so now let's summarize. So this is just in your scratch paper. Okay, so for this one, so now we take delta to be the minimum values of 1 and epsilon over 19. So you can see this kind of where these kind of mystery numbers from, right? If we take delta to be the minimum values of 1 and epsilon of 19, therefore x minus 2 less than delta for this number, okay? For this region, for this one, then x must be x minus 2 must be less than 1, right? Because the delta is the minimum values of 1, right? If you're less than delta, of course, less than 1. Okay. So, and another one, 19 times x minus 2 should be less than epsilon, right? Because x minus 2 is less than delta. Delta is less than equal to epsilon over 19. So times 19 would be epsilon. Okay, I draw the right one. Then this one is less than 19 times, yeah. Okay, again. So this one is less than delta. Delta is less than equal to 1. So it's less than 1, right? And this one is less than because x minus 2 is less than delta. So it's less than 19 times delta. And now delta take to be the minimum values of these two numbers. So it should be less than equal to 19 times epsilon over 19, right? At most is epsilon over 19, maybe smaller, right? So this one is less than, this one is equal to epsilon. So in other words, 19 times the absolute value x minus 2 should be less than delta, and less than epsilon, okay? So with this help, then we can say, so we take this delta to be the minimum value of 1 and epsilon 19 for this x minus 2 less than delta, x cubed minus 8 is always less than equal to the absolute value of 2. Let's just rewrite again, right? 2x plus 4 times x minus 2, right? And this one is less than 19 because it's less than 1. So if you expand it less than 3, right? You plug in 3, it would be 19. It's not less than equal to, it's less than 19 times x minus 2. And from the discussion here, so this one is less than equal to epsilon. This one is less than epsilon. Then we are done. Okay, let's summarize it. How to prove it? For any epsilon greater than 0, right? There exists delta, which is the minimum value of 1 and epsilon over 19. For x minus 2 less than delta, f of x minus f of a, which is f of 2, which is less than epsilon, which is exact the same as the epsilon delta criterion, right? Any epsilon greater than 0, there exists the delta. For x minus a is less than delta, f of x minus f of a would be less than epsilon. Okay, right? So here our a is 2. Here our delta is 1 minus 1, minimum value of 1 and epsilon over 19. Okay, so you can see that from this example, you can see that this delta, depending on the choice of epsilon, also depending on this position 2, right? Because this 19 is from this position 2, right? X minus 2 is less than 1. So from this one, this is the remark. This epsilon, this delta. The choice of the delta depends on the choice of epsilon and the position A. Okay. So now let's look at another example. F of x which is equal to negative x and x minus 1 when x is less than or equal to 0, when x is greater than 0. This one does not satisfy the epsilon delta criterion at 0, x equals 0. Okay, we can draw the graph. Less than or equal to 0, which is negative x. Negative x is greater than 0, which is x minus 1. X minus 1. So this is a negative 1. When x equals 0, it's equal to negative 1. Okay, so I say at x equals 0, this is 0, right? It does not satisfy this epsilon delta criterion. Okay, so here I use the graph to help you to understand. So that means from the graph, okay, if it satisfies the epsilon delta criterion, you can find some term box, right? Such that this curve will enter the box from the sides, one side, and leave the box from the other side, right? So if we take epsilon to be 1/2, okay, f of 0 equals what? F of 0 equals 0, right? F of 0 equals 0. So 1/2. So here is f0 plus 1/2, which is here. This is 1/2, right? And this is another 1/2. F of 0 minus 1/2. So it's negative 1/2. So you can see, can you draw the box? This is the center. Can you draw the box to make the graph in this box, which is from one side to the other side? No. This one is outside, right? Okay, it entered the graph at the box from one side, but at the other side is outside, which will not be totally inside. Okay, so it does not satisfy that condition. You cannot draw anybody. How small you can draw? No, you cannot make it, right? Any small, no matter how small you have. This part always be outside the box, okay, will not be inside the box. So the difference must be greater than 1/2, right? Okay, so for this epsilon, so there is no delta greater than 0, such that this is delta, right? This is 2 delta, 2 delta. Oh, this one is also another 2 delta, right? The center is here, so this is the delta minus delta, and this is the plus delta, right? Based on the box you have, maybe here and maybe here, doesn't matter. No matter how the box you make, it always cannot satisfy this condition. So there is no delta greater than 0 such that this f of x minus f of 0 would be less than their 1/2. So in other words, there's no delta such that this f of x is between negative 1/2 and 1/2, right? The f of 0 equals 0. So the absolute value of f(x) is less than 1/2, so it's between negative 1/2 and 1/2, right? Between negative 1/2 and 1/2. So on this, no matter how small you have, you always have some values here, right? So in other words, so there exists some x, okay, which is in the x minus 0 less than delta, this x, right? F of x is always less than negative 1/2. Not greater than negative 1/2, because here, right? This kind of x, this x here, for this x values, it always be less than negative 1/2, not greater than negative 1/2. Right? So that means it's outside the box, right? Okay. So this example tells you the definition for a function does not satisfy epsilon delta criteria. Okay, so what's that? Let's look at the remark. So we say a function f first does not satisfy the epsilon delta criterion at A. It means for any epsilon, there exists some epsilon greater than 0. For any delta greater than 0, there always exists some x which is between a minus delta and a plus delta. That means x minus a is less than delta for certain x, such that f of x minus f of a is greater than or equal to epsilon. So does not satisfy. So satisfy, then there exists becomes for any. Right? For any becomes there exists. Right? For some becomes all. Right? Okay. So if it satisfy epsilon delta criterion, that means for any epsilon greater than 0, there exists delta x. And for all x in this interval, that means x minus a is less than delta, right? Such that then you must have for all the x inside, this f of x minus f of a must be less than epsilon. So this means the satisfy the epsilon delta criterion. If it does not satisfy the epsilon delta criterion, it says, okay, for there exists a certain epsilon, okay? For any epsilon, any delta, no matter what delta you choose, it's positive delta. For this interval, we can always find some x values such that this f of x minus f of a is greater than this epsilon, which is exactly this one, like this example. We take epsilon to be a specific value, 1/2. Of course, you can take it to be 1/4, doesn't matter, okay? You take 1/2 here, then there is no delta, right? So that means for any delta you can take, it always, or can always find x, which is on this interval, right? On this interval, this f of x is always less than 1/2. So take the epsilon would be greater than 1/2, right? That is the things. Okay. So here is from, this is the example for does not satisfy the epsilon delta criteria. And this example show that it satisfies the epsilon delta criteria. So so here is a hint, okay? Hint for using epsilon delta criteria. Okay, so when you try to prove something satisfy some function satisfy epsilon delta criterion, you need to rewrite. The first thing is you need to rewrite this f of x minus f of a. This one is less than equal to or less than, doesn't matter, something, some constant c, okay? Something, some constant c times x minus a. Okay? Sorry. Sorry. Yeah, it's correct, but I should see one more thing. Write this one as something times x minus 2. Okay? Then we replace this is something with an upper bound for example m, okay, capital M, upper bound capital M. For x on some intervals, which is a minus r and a plus r. Okay. And then you take epsilon delta to be the minimum values of epsilon over m or this R, then we are done. Okay, so like we did here. This example, let's review again, okay? We write f of x, this is f of x, right? I use a color. This is f of x minus f of a, right? Which is equal to something times x minus 2, right? Times x minus 2. Then, of course, we want to find some bound, upper bound for this term, right? This one is bounded by this one. But it's not a fixed number. So we consider this region, R, to be 1. We take R to be 1 here. Right? R to be 1. R to be 1, then it becomes, it's 2 minus 1. This is 2 plus 1, right? A minus R, A plus R. And this one, on this region, we have some upper bound for this term, which is given by 19, right? This is the largest number you can take. Upper bound, you can take 20, it doesn't matter, right? But this 19 is the thing we calculate, right? So we take the 19 as our upper bound. So we can write this one as its upper bound f of a. This is the fx, sorry. This is fx minus f of a is less than the upper bound times x minus 2, right? Then we take the delta to be epsilon over this upper bound, which is m, right? This is the minimum values of the epsilon over its upper bound. Here is 19. Or the R here we take to be R to be 1, right? Here's 1, this 1. So, 1. Right? Or 1 here or R here. We take the minimum values of these two, then you can do this kind of calculation, right? This using the inequalities until you get the epsilon. Okay, so this is a very standard steps when you are asked to prove certain functions satisfy this epsilon delta criteria. So this is the hint. Okay, always use these steps. So the hard part is one thing here, less than R. You should make this one to be a constant times x minus 2. Sorry, it's not an x minus 2. Yeah, it should be x minus a. Here is x minus a. A equals 2 in that example, right? Okay, always start from here on your scratch paper. Okay. Yeah, so after class, you need to go back to read that example again. It would be helpful. So today we want to, yeah, we can stop here. So next time, we want to show this example. I give you the theorem first. Theorem 3.20. It says f is continuous at x equals a. So this is the as defined. What's the continuity means here is as defined in terms of the sequence, right? In terms of sequence. If and only if f satisfies the epsilon delta criteria. Okay, so this theorem, so this is since this is the if and only if problem. For any if and only if problem, you always needed to prove two directions, right? Two directions. If you know x is continuous, then you needed to prove f is satisfies epsilon delta criteria. This is the one direction. The other direction, if f satisfies the epsilon delta criteria, then you needed to prove f is continuous at A using this definition, the sequence. Okay. So this is the if and only if problem. So that means these two statements are exact same. F is continuous at A. That means F satisfies this criterion at A. Okay, so let's, before the proof, let me give you the remark for this one. So this is a new definition. For continuity at A. Okay, this is a new definition for the continuity there because they are equivalent, right? This theorem tells you they are exact same. So we can say that, okay, we say that F is continuous at X equals A if for any epsilon greater than 0, there exists a delta greater than 0 such that for x minus a is less than delta for all this kind of x on this interval, f of x minus f of a is always less than epsilon. Okay. So this is a new definition. And you will see in your calculus book, textbooks, you will always use this definition. But for our book, we introduce this one as another one, right? As another definition. And we use the sequence to define the continuity at first, because it's easy to understand. Okay, and this is the one which is called, we use the epsilon delta language to describe the continuity. And this continuity is the one we often use, okay, in many cases. Of course, we can still use this original definition using the sequence, okay, but sometimes we like to use this one. And you will see in other textbook, when they try to prove a function is continuous, they always like to use the epsilon delta language. Okay, so we stop here. So next time we will continue. Okay, continue this section. We will spend 2 classes on this section. Okay, so we stop here. Any questions?